Modern frontier AI models are staggering in their raw capability. If you need a complex application coded from scratch, these systems can generate functional, elegant architecture in a matter of seconds. But drop that exact same model into a complex enterprise environment, and the results often shift. It might output beautifully formatted reports that are either completely generic or worse, confidently wrong. These inaccuracies stem from a lack of relevancy. While the model's reasoning engine is sound, it lacks the specific internal details of your business. To fix this, we rely on a discipline called context engineering. This is the infrastructure built around an AI to discover the right data, understand its meaning, and feed it to the model at the exact moment of execution, all while obeying strict operating rules. You cannot just plug a large language model into a corporate network and expect miracles. Organizations have to build a rigorous, multi-layered system around the model to manage its context. Adding more parameters or switching to a slightly larger model will not turn generic outputs into actionable intelligence. The bottleneck is no longer raw reasoning power. The bottleneck is context. Let's look at the reality of enterprise data. This is the data estate. Information is siloed and scattered. Some sits in highly structured relational databases, some in messy document stores, and the rest is spread across SaaS APIs and on-premise mainframes. The traditional approach to analyzing this information was to copy everything into a single centralized data lake. But because business data changes by the hour, this method creates constant synchronization delays. The first pillar of context engineering solves this: connected access. The AI needs visibility across the entire estate, natively. Rather than moving the data to the model, we use zero-copy federation. The AI sends queries out to data exactly where it natively lives. Because we aren't constantly copying and migrating terabytes of files, the information the AI pulls back is immediately current. It reflects reality up to the second. Furthermore, the original access controls of those native systems remain completely intact. If a user's prompt triggers a query into a restricted HR database, the native security protocols block it right there at the source. Without connected access, an AI assistant is either operating on stale information or it is bypassing your security protocols before it even begins to process a prompt. While connected access reaches the data, raw bytes and unstructured text alone do not provide useful context. That requires the second pillar, the knowledge layer. This is the system responsible for giving your scattered enterprise data semantic utility. A core mechanism here is entity resolution. This process takes disparate, messy data points from across different databases and maps them to single, unified concepts. Once identified, the layer draws out the hierarchies and maps the relationships. It understands, for instance, that a specific corporate client profile is directly linked to an isolated technical support ticket filed 3 weeks ago. Beyond basic semantics, a mature knowledge layer embeds institutional knowledge directly into the data. It preserves historical decision traces so the AI understands why a past action was taken. This converts disconnected files into a structured, navigable map. With the data connected and mapped, the model needs a way to pull exactly what it needs. This is the third pillar, precision retrieval. Providing better context does not mean giving the AI a larger volume of data. It means giving it highly filtered, intent-driven data. The baseline method for doing this is standard RAG, or Retrieval-Augmented Generation. This visual represents a vector database. In standard RAG, we take source documents, chunk them up, and embed them in a three-dimensional mathematical space. Here, the text is plotted based on semantic similarity. When a user inputs a prompt, that query acts as a target, drawing in the nearest cluster of mathematically similar document chunks for a single one-shot retrieval. This is highly efficient for simple lookups, like founding a policy in an employee handbook. But one-shot retrieval struggles with complex enterprise tasks that demand multi-step investigation. To handle that complexity, retrieval architecture has evolved into Agentic RAG. Agentic RAG is an iterative process. The AI makes a first-pass query to retrieve initial data, and then it pauses to critically evaluate those results against its overall goal. If the agent determines the initial data is insufficient to formulate a complete answer, it actively initiates secondary and tertiary loops, going back to the database array to search for highly specific missing information. Agentic RAG transforms retrieval into an active investigation, where the system autonomously manages its own context gathering. Another advanced retrieval method is GraphRAG, which moves away from flat semantic similarity in favor of structural, relational navigation. Instead of just looking for matching keywords, GraphR examines entities and connections first. It asks what nodes are structurally connected to a specific subject before it even attempts to read the underlying documents. Only after tracing the correct relational paths does the system apply a vector search. The search is strictly constrained to the boundaries established by the graph, delivering a highly precise subset of information. But retrieval is only half the battle. Before this data reaches the model, it must undergo context compression. Even with the massive context windows available on modern frontier models, excessive noise mathematically degrades performance. Systems must compress, summarize, and prioritize the retrieved inputs immediately prior to inference. By pairing highly structural retrieval methods like GraphR with aggressive compression, you ensure a maximum signal-to-noise ratio. The model only computes what truly matters to the query. This brings us to the fourth and final pillar, runtime governance. This is the mechanism that ensures the entire architecture is legally and operationally safe to deploy. Governance cannot be a static set of rules checked once a quarter. It must be enforced live, operating as a real-time checkpoint exactly at the moment of retrieval and again at the moment of response. Consider an enterprise analyst asking their AI assistant to generate a comprehensive preparation document for a major upcoming client meeting. The system springs into action. It retrieves recent technical support tickets and past deal renewal history because those documents are contextually and relationally tied to that specific client. During this sweep, the search also uncovers internal executive pricing discussions. However, the system actively blocks the specific stream from reaching the model. The querying analyst lacks the role-based access required to see pricing data, so the system stops it cold. This live enforcement creates a defensible system. The AI's output is strictly bounded by the exact operational permissions of the human operating it. Looking at the complete architecture, the structural requirements for enterprise AI become clear. The foundation is connected access, which grants visibility. The knowledge layer grants meaning. Precision retrieval guarantees relevance, and runtime governance guarantees security. Rather than returning beautifully formatted but generic guesses, an AI supported by this pipeline delivers highly specific, accurate, and fully governed intelligence. An AI model's intelligence is strictly capped by the quality, accuracy, and legality of the context it is permitted to access. Raw reasoning power is now ubiquitous. The true differentiator for enterprise success is building contextual intelligence. As we move toward fully autonomous agentic AI, these systems cannot function safely or effectively without this meticulous, structural foundation locking everything into place. Deploying frontier AI in the enterprise requires a shift in focus toward the infrastructure surrounding the model. Success requires prioritizing the engineering of context.
Thank you. Share and subscribe to Learn AI for more AI insights.